Welcome to Basics of Neuroscience. Today, we're exploring one of the most fascinating and mind-bending phenomena in human biology, phantom limbs. Imagine losing an arm, yet still feeling its presence so vividly that you try to pick up a cup with it. Why does this happen? What is the brain doing? By the end of this lecture, you will understand the incredible adaptability of the human brain and the mathematics behind how it rewires itself. Let us dive in. To start, imagine unplugging a computer mouse, but the cursor still moves on the screen for a few seconds. The hardware is gone, but the software still registers it. This is exactly what happens in the human brain when a limb is amputated. A phantom limb is the vivid, undeniable sensation that a missing limb is still attached and moving. It is crucial to understand that this is not a psychiatric delusion or a trick of the imagination. The brain has spent a lifetime receiving signals from that arm or leg, and it does not simply delete that programming overnight. Now that we know what a phantom limb is, let us look at the underlying neuroscience. The root of this phenomenon lies in the brain's somatosensory cortex, which processes touch and feeling. When a limb is removed, the severed nerve endings continue to send random, spontaneous signals. More importantly, the specific area of the brain that used to process signals from that missing limb suddenly becomes hungry for input. To survive, it starts rewiring itself to receive signals from adjacent body parts. This incredible rewiring process is called neuroplasticity, causing the brain to misinterpret new signals as coming from the missing limb. Understanding this rewiring is absolutely crucial because it completely revolutionized neuroscience. For decades, doctors believed that the adult human brain was strictly hardwired, meaning it could not change its physical structure once we grew up. Phantom limbs proved this wrong, showing that the brain is highly plastic and constantly adapting, no matter our age. In real-world medicine, this knowledge is a game changer. It helps doctors treat severe phantom limb pain, which affects up to 80% of amputees. It also guides the development of advanced robotic neuroprosthetics that wire directly into the nervous system to provide real sensory feedback. This brings us to an exciting intersection of biology and mathematics. To truly understand how phantom limbs occur, we can mathematically model how the brain's map, or homunculus, changes over time. The formula is A new equals A old plus R times delta t. Conceptually, this calculates how much adjacent brain tissue expands into the unused space. A new is the new cortical area. A old is the original area before amputation. The variable R is the rate of cortical remapping, telling us how fast the brain rewires. Finally, delta t is the time passed in months. If the rate or time increases, the adjacent area takes over more territory, leading to more intense phantom sensations. Let us see this formula in action with a clinical example. Suppose a patient underwent an arm amputation. In the brain's map, the face area is next to the arm area. The original face area, A old, was 400 square millimeters. MRI scans show the face area expanding into the missing arm's territory at a rate R of 15 square millimeters per month. We must calculate the new cortical area after 6 months. We substitute our known values into the equation, replacing A old with 400, R with 15, and time with 6. Following the order of operations, we multiply 15 by 6 to get 90. Over 6 months, the face map has taken over 90 square millimeters of the amputated arm's area. We add this to the original 400. The final area is 490 square millimeters. Physically, touching the patient's face now activates the old arm area, making them feel their missing arm. To make this completely clear, let us look at a diagram of the brain's somatosensory cortex. You are looking at a cross-section of the brain. Notice the region labeled original face area, shaded in blue. Right next to it is the amputated arm area, shaded with diagonal lines to show it is no longer receiving normal input. The large arrow indicates the direction of cortical remapping. It shows the face area physically expanding downward into the silent arm territory. This visual perfectly captures what our math just proved. The brain dynamically rewires itself, allowing adjacent active regions to invade and take over deprived sensory maps. Now that we understand how the brain's map changes, we must address a darker side of this phenomenon: phantom limb pain. Why does a missing limb hurt? The answer lies in a mismatch of signals. When you move your intact hand, your brain sends a motor command, and your eyes and nerves send back sensory feedback, confirming the movement. In an amputee, the brain still sends strong motor commands to the missing limb, but it receives absolutely no sensory feedback in return. This massive mismatch between what the brain expects to feel and what it actually feels creates an error signal, which the brain interprets as severe, cramping pain. We can actually model this pain intensity using a simple mathematical equation. The formula is P equals K times the quantity M minus S. Conceptually, this calculates the exact difference between the outgoing command and the incoming reality. P represents the perceived pain intensity. M is the strength of the motor command sent by the brain. S is the actual sensory feedback received, which is often just random nerve firing. Finally, K is a sensitivity constant, unique to each patient's nervous system. If the motor command M is high, but the sensory feedback S is extremely low, the resulting mismatch is large. This large error is directly multiplied by the sensitivity constant, resulting in high pain. Let us apply this mismatch model to a specific patient scenario. Imagine a patient trying to clench their phantom fist. They send a strong motor command, so M equals 80 units. Because the limb is missing, the sensory feedback S is only 5 units, coming from random nerve firings. The patient's sensitivity constant, K, is 0.2. We need to find their perceived pain intensity. Our strategy is to calculate the difference between the motor command and sensory feedback, then scale it by the sensitivity constant. We plug our values into the formula. Subtracting 5 from 80 gives a mismatch of 75 units. This large number shows the brain is highly confused. It shouted a command, but heard nothing back. Next, we multiply this mismatch of 75 by 0.2. The final pain intensity is 15 units. This proves mathematically that a larger gap between expected and actual sensation directly causes higher pain. This mathematical understanding of pain mismatch leads directly to one of the most brilliant treatments in neuroscience: mirror box therapy. If pain is caused by a low sensory feedback value, S, how can we increase it when the limb is gone? Doctors place a mirror vertically in front of the patient. The patient looks at the reflection of their intact, moving limb, which creates the visual illusion that the phantom limb is moving perfectly. This visual trick artificially increases the sensory feedback variable S in our equation. By raising S, the mismatch between motor commands and sensory feedback shrinks, which successfully lowers the pain intensity P. We have covered a tremendous amount of ground today. Let us review the key takeaways. First, phantom limbs prove that our perception of our body is an active construction by the brain, driven by neuroplasticity, not just a passive reflection of reality. Second, we learned that cortical remapping can be modeled mathematically, showing how active brain areas expand into deprived territories over time. Finally, we saw that phantom pain arises from a mismatch between motor commands and sensory feedback, a gap that innovative treatments like mirror therapy aim to close. You now understand both the biology and the mathematics of the adaptable human brain. Excellent work.